So hello everyone. So I'm really happy to be able to talk about R with people from the other side of the globe. And like Amy mentioned, I'm joining you from Lithuania. And currently here it's a bit of a middle of the night. So if I'm not as smooth as I probably should be, I hope you can take that into account and forgive me. So my talk will be about lesser used base R features. And by lesser used, I really mean things that you wouldn't stumble upon by, for example, taking R courses or even reading contemporary books about R. One note before we begin is that I will assume in this talk that you are not a complete R beginner. Otherwise, you might miss a few things. If that happens, that's fine. I will talk about 4 different topics. So if you find yourself not really following one topic, you can just wait till the second section starts and go from there. So with that said, let's begin. The first topic I would like to talk about are these infix and replacement functions. And you might find this topic interesting if the 2 lines here, the 2 first lines of code on the slide seem kind of friendly to you. And maybe the 3rd one gives you a pause and you are a bit weirded out about it, or maybe intrigued. So if that's the case, I hope this will be helpful. So for a bit of context, let's go over the replacement functions. In R, there are these things called replacement functions, and you write a replacement function with this syntax. Basically, you have to have a special function name that ends with the assignment symbol. And when you have this function, you call it by doing an assignment to your function call. And what it does, it replaces something about X with what's in value. And in base R, we have some examples. So for example, there is a names function that changes the names of an object. You can also change the class of an object. And there are a lot more. So one may be a bit exotic is this last one where you can change the first and second element of X into NA, also with this kind of syntax. So next thing that you are probably already familiar with is this infix operator syntax. Again, these are special functions and they have a special name. If you try to implement this function, you have to use this percentage signs around your function name. Once you have this function, you call it by putting your infix operator in between 2 variables, and the function will do something for those 2 variables and provide you with a result. In R, there are a few examples of those functions. So one very well known is the in operator, which checks if the element in set also appears in X. And there is also this one called outer, which basically takes a multiplication of every pairs of elements. So for example, that line, the last line of the code would provide a multiplication table. But the surprise begins when you try to combine these things. So in R, you can also write this very special function, which combines both infix syntax and replacement syntax. You do this again by having a special function name. It has both the percentage signs around the function name, as well as a assignment operator at the end. Once you have this function, you would call it like this. So you would have an infix in between your variables, and then you would assign a variable to that statement. And what it would do is it would replace a value in X based on the comparison between Y and X. So, and the surprising thing is that even though this is a valid R syntax and R allows us to construct these things, there are no examples of such functions in base R. So since there are no examples, we can now look at some of them. So this is a very simplistic one, a function you can write in R. If you look at the body, it's doing a very simple thing. It checks if Y elements are in X, and for every such element, it replaces the value in X with an optional value from this function. So just an example of how it would be used. If you have a vector with 4 elements, you can write your call like so. So you write vector, which is your variable, and then basically a standard in operator that checks if B and C is in vector, and then you assign a new value to those values found in the vector. And what it would produce is it would replace the vector, it would replace the values B and C, in this case with O. And even more surprising is you can do this not only with your custom infix operators that use, for example, percentage signs, but you can also do similar things with standard operators. So like in this example, we are using this equals operator, which just compares if two values are equal. But I can also add an assignment to the end of this function. And then if I have a vector now, the same vector, about 4 elements, I can call my new function like so. So I say, okay, vector equals 3. I found all the values that are equal to 3, and I replace them in this case with a 0. So what that would do is it would find elements that are equal to 3 and replace them with 0. Yeah. So after finding this functionality, I got in contact with this other person. And again, now I might mispronounce the name. So it's Antoine Fabry, as far as I know. And we worked together to create a package that basically utilizes these things. It was quite surprising that we were not able to find it used anywhere, even in external packages. So we call this package called inops. And just like a quick example of how we exploited the syntax. So in this package, we created basically a big list of various infix assignment operators. So for this example, here we have this vector of countries like USA, China, Russia, Latvia, and Lithuania. Now, we provide various operators, and one that I particularly like is this one which checks for elements that occur a specified number of times in the vector. So for example, if we call something like that, what it would do is it would return true only for elements that occur once in the vector. So USA occurs 2 times, China occurs 3 times, Latvia and Lithuania occurs only 1 time. So it would return true for those. Next, we can also use selection. So if we add this bracket in the beginning of our operator, we would actually select those elements. And now we also provided this new syntax that we found, which is useful for replacement. So if you write it like this, then what this would do is it would replace all the elements that occur only once within your vector with the other group. So for example, if you're doing some kind of analysis and you have many groups and you want to group all the smaller groups into one group called other, the syntax would do this in one line. Yeah, so that package has a lot of various different operators, and if you care about this thing, you can check it out. For example, we have some that work for regular expressions, for interval comparisons, and various things like that. So now moving on to the second topic, in R, there is this thing called the dollar operator. And you might find this part interesting if you feel good about the first 2 lines here, which uses the dollar operator and also auto-completion after pressing the tab key. But you are surprised that you maybe also make the tab key fix spelling mistakes for you. And if that's the case, then this talk might be interesting, this part of the talk. So yeah, let's start with explaining what the dollar operator is. So let's say we have a vector of 3 elements and the vector has names 1, 2, 3, right? The dollar operator typically works on lists and data frames. So if you would try to do something like that, it would give us a syntax error, basically. It's invalid for atomic vectors. Okay, but we can do one trick here. We can bless our vector actually with another class. So we, instead of only just being numeric, we say, okay, this vector is now not only numeric, but also has another class, which is my class. And then R provides us with this generic function dollar symbol. And this function here is really simple, right? So you have a dollar symbol for a class of type myClass, and we passed it x and name, and it simply selects that name from that x that we passed it to. And you can think about it like that. So if you write this expression in red on the right side, x dollar name, and press enter, then this function will get executed if x is of the right class. So if we now write vector $2, it will select the second element. So we made it work on our vector, our special vector in this case. But it can also be used for other things. So it can be used to do computations, not only to return elements to you. So if you now modify our function like this, what we end up with, we would not only select elements from X, but we would use the part after the dollar operator to call functions on our vector. So as an example, having a function like that, if you now call vector sum, what it would do is it would call the function sum on all the elements of the vector, and they sum to 6 here, so it would return 6. So that's surprising, okay, but there is also this part about autocompletion. So we have this vector of a new class, right? And we can call functions in it with this new dollar operator, but it for now doesn't automatically complete the names because it doesn't know what to complete. And here R has this second generic function, which might be useful, which is called dollar names. And dollar names, basically you can think about it like this. You have X, an object, you type dollar operator and start typing a pattern, and then you press the tab key. What it does is it passes X and pattern into this function, and whatever this function returns is then replaces the pattern. So here, just as a simple example, if you look at the body of this function, we create a vector of 3 character strings, basically mean, median, and sum. And then we use pattern to select one of these 3 values. So if somebody will start typing one of these 3 values, they will get autocomplete. So how this works, if we now add this new function to our R session, and we start typing back $s and press the tab, it would autocomplete to sum. And in another case, if instead of S, we started typing ME, press tab, it would see that there are 2 possible occurrences. So it will show us both mean and median. Yeah, but it doesn't have to be, this function doesn't have to make sums. So really you can put anything in there. So as a very simple example, for example, you can modify this function to always return a string whatever. And now whatever we write after the dollar operator, once you press the tab key, it will simply replace whatever was there with whatever. Or even more weirdly, what we can do is not only return character strings, but also do something crazy like maybe starting a new plot. And now if we have such a function, if we start autocompletion, press tab, it would actually show us a plot and we would have written whatever on that plot. So basically the takeaway is that you can transform this function to do anything, not just actually provide you with autocompletion. And where can this be used, for example, in practice, besides, of course, writing your own custom classes, is it can be used to modify how autocompletion works for data frames. So if we now write this function $names.data.frame, we will be implementing a generic for the data frame class. And here I try to use this agrep function. And agrep is very similar to grep. It tries to look for patterns, but it's not really exact. So you can have mistakes in there. So if you, for example, looked at the 3rd argument there, max distance, it specifies how much of a mismatch the function tolerates. Then we also add ignore case because we want to autocomplete even if we put the wrong case there, and value equals true, just so it returns the value to us. So anyway, if we put this function to R, and then we start with this famous iris dataset, press the dollar operator or start typing something closely resembling one of the columns like Z, P, C, press tab, and it will correct our mistakes, and it will know that the closest column to what we wanted to find is PCs, so it will autocomplete. Yep, so that's about dollar operator. Now, the next thing is plotting hooks. Now, you might be familiar with the concept of a hook if you use packages like maybe knitr, but you might be surprised to find that base-R also has this concept, and it uses it in a few places. So here we will see as an example hooks introduced into plotting operation. So like I mentioned already, hooks is a mechanism for injecting function after a specific action within R takes place. So if you looked at for the code for the function plot new, you would find that there are two hooks defined there. So within the first loop, you can see that it calls get hook before plot new, and this get hook method would extract all the functions defined in that hook, and this loop then would iterate over all those functions and call them in turn. And likewise, you have, after the plot is created, the second hook, plot new, which does the same, but only for a different hook now. So we will just create a simple example to demonstrate how this works in practice. So let's say we have a simple function add date. This is base R function, so it's base R plotting. And what it does, it adds the current date on top of the plot you're creating. So this mtext is marginal text, and it puts system date in the margin on the top of the plot. Yeah, simple function. And then we call this set hook mechanism. So how it works is we provide the hook we want to set, in this case plot new, one of those plot hooks. We provide our function we want to add into that place, and we said append. So if there were any functions before us, we would not replace them, but append to them. And now after we've done this, we can call, for example, plot or pi. And the result would be that you can see that on the top right corner there, now there are these dates printed on the plots. And whatever plot I do in this session from now on will always have the date on top. So that's a hook. And when I found this mechanism, I kind of thought, okay, how can I exploit this? So I think I came up with is that it can be used to provide a theming system, a very convenient theming system for base R plots. So I created this package basetheme just to test if this works. And on the left side here, you see a default pairs plot, which is a simple plot in base R that provides scatter plots for all pairs of variables. And on the right side, there is the same plot after you change the theme using this hook operation. So the concept of this package is very simple. I basically add functions that change graphical details, and I then add them to the hooks before the plot is called. So whenever somebody produces any kind of plot, they will always call that hook just before the plot, and it will set various graphical parameters before the plot appears on the screen. So just a quick another demonstration. Imagine you have some kind of a report that looks maybe something like this. What it allows you to do is set the theme once, and then it will apply that theme to whatever plot you do in R, in base plot, not for grid package. So, for example, if you got bored of this look, you might say, okay, maybe I want to try another theme, and all you would have to change is that one call. You change the name, different theme will be applied to all of your plots. And this is persistent, which means you don't have to apply a theme to each plot. You set it once, and the hook is there, and it will work from now on in that R session forever until you close R. So that's how I try to exploit this mechanism. And the final topic of this talk is the Bayes plotting itself. So many people, even if they use ggplot actually, sometimes they do a plot or two in Bayes plotting because there are some functions that are maybe more convenient. So if you are that person and you, for example, know about functions like plot or hist, but are a bit confused about maybe the last two lines, you might find this part interesting. So if you go over a new user's experience with Bayes R plotting, we can imagine it to be something like that. They have a goal, like maybe they want to create a very minimal picture that has a histogram on top of a density plot. And they would probably go about it like that, right? They find that you can plot density objects directly. So they start like that. And okay, so they now don't like that title. They want it removed. So they find there is an argument which turns off the main. But they maybe want to do the same for all the access labels actually. So they find two additional arguments, okay. But there is still too much in this plot. They want it to be minimal. They want just the density lines without this access. So they find a way to turn off them as well, okay. Now they find another function called hist. And they think, okay, if I call hist, it will be added on top of my density function, but it's not the case. And actually they, at this point, would be confused why you call plot to plot density, but there is a special function, hist, for histogram, why it works a different way, right? Okay, so they now replace their plot, but they wanted to add on top of it. So maybe they, will search Stack Overflow and find that there is this parameter add equals true, which adds on top of the plot. Okay, so now it's added, but the histogram is too big. After another search on Google or someplace, they might find another parameter, which is freq. And that makes histogram bars resemble the values in the density plot. That's fine. Maybe they also like more breaks, so they find parameter for that. And now they still see that, okay, the plots are on top of each other, but the histogram hides basically the density plot. So maybe they find some colors, adjust transparency, and now it shines true. They can even increase the line size of the density plot. Okay, that's fine. One more thing is probably that it looks like the histogram goes over the top of the plot. So they manually adjust the y-axis limits. And okay, looks like right now they have their plot. But if they remember this experience, they would think of Bayes plotting as being kind of really bloated and weird. And my God, if I actually wanted to add more than one histogram on top of here, it would be hell, right? I would have to, again, call one function, set add equals true, and somehow align all these bars within them. It's basically tough and it's clunky, right? You not really are working with Bayes graphics at this point, but more so fighting against them. The files that you get do too much and you spend a lot of time trying to turn them off, basically. Yeah, so your conclusion would be that, okay, Bayes R graphics is bloated, unintuitive, weird, and hard. But maybe, not so fast here. So I will try to defend Bayes graphics a bit during this part. So one thing to state outright is that those plots like plot, hist, they are really wrappers. So they are very high level functions. And under the hood, they call a lot of small functions that are really intuitive and work very well with one another. So let's take a simple example. If you do this, like plot 0, 10, 0, 10, you will get a scatter plot, a simple scatter plot. But even this plot is actually, like I said, a wrapper around a lot of different things. So if we were to reconstruct this one by one with the actual functions that do all the work, we would see something like that. We'll first start with the plot new, which just creates a new empty plotting device. Then we would call another function plot window. And this plot window overlays a coordinate system on top of our new device. So if you want to add a point on top of the plot, we need to know which place of the plot corresponds to which x and y coordinate. So we basically add Cartesian coordinates on the plotting region with this function. And then we can start adding things on top. So for example, we might do points and it will add points. Then we can create an axis. So axis 1 for the x-axis, axis 2 for the y-axis. And actually here, you might wonder about the numbers, what those 1 and 2 means. So 1 basically refers to the bottom of the plot, and the numbering goes clockwise. So 1 is the bottom of the plot, 2 would be left side, 3 would be top, 4 would be right side. And these numbers are used throughout various different parameters. So here we use them with axes. So we had axes, then okay, there were also a box around the plot, was also a box around the plot. So we added with another function called box. Then titles are missing. So okay, we had title, my plot, okay, a title for the x-axis and title for the y-axis. And we recreated the plot we had before. But now, when we put it like this, everything becomes really clear. For example, if you have a friend who doesn't know anything about programming or maybe even anything about R, and you ask him which line does what on this plot, they would have no trouble telling you. Axis is added by axis, points added by points, box around the plot added by box, titles added by titles. So once you have it like this, we might try changing a few parameters. So what we would do is maybe, okay, what can we do? So we can add grid to it with the function grid. Now we have a grid. We might say, okay, we can adjust the title. Like if you look between these two, the title moved to the left. Then, okay, maybe we increase the font of the axis numbers. Maybe we don't need the box around the plot. We turn it off. We might say, okay, we don't need these axis lines anymore. They're nice. We can make the axis labels maybe a different color. We can increase the point size and stuff like that. So you of course would need to know the parameters, but it's trivial to see which line has to be modified in order to change certain elements. Yep, so after this, okay, so at this point you would, a takeaway would be that in base R, you call these small little functions to do all the work within the plot. But there are tons of different types of plots, right? There are box plots, bar plots, histograms, density plots, and whatnot. And you would think that, okay, if I'm using these really small functions to produce these plots, do I really need to know hundreds of those functions? And it turns out that a set of things you might want to do for a plot is really quite limited. So here I tried to provide a set of functions that would be quite sufficient to produce almost any kind of plot. And in the next slides, I will try to demonstrate how you could use those functions to really recreate the plots you want to see. So just as a simple example, here we first create a checkerboard pattern. So we create some variables. Don't worry about these too much, but these are basically the centers of the rectangles. We will have many rectangles on the checkerboard, and each of these rectangles will have an x coordinate and a y coordinate. So those two variables just called that. Then there is a bit of a boilerplate, which is always has to be done. You always have to request a new plotting window, and you always have to set the coordinate system on that window for any plotting to be done. So that this does that. And then with just one function called to this function rect, which draws a rectangle, you can produce, or you can actually draw all the rectangles in a single go. So this function accepts just a few arguments. Basically, you provide coordinates for the lower left side of the rectangle and the upper right corner of the rectangle, and it draws a rectangle. And if you provide many, it will draw many. So with a single function call, which is vectorized, we can add a lot of objects of the same type on the plot. Now, moving on to a more realistic example, for example, bar plot. Here, we will try to produce a bar plot for US population growth. So again, we extract the needed variables to X and Y just for convenience. So X here would be time in years, and Y would be population, I think, in millions. Now, once we have that, again, we have our boilerplate code, which is give me a new plotting window and set the coordinate system. After that, we can start producing the plot. So in this case, we want a bar plot. What do? We call rect, basically to draw a rectangle for every population value for every year. We already have a thing that resembles a bar plot pretty well. Then we might want, for example, to add the actual values in text on top of each bar plot. And here, text function does that. And there is this pos equals 3 argument in the fourth position. And the 3 again just specifies the position, like I mentioned with the axis. 1 is the bottom, 2 is the left side, 3 is the top. So we want the labels on top. So we say 3 and they will be on top of the actual values. Finally, we add the years as an axis text, and also the actual values for the y-axis as the axis text. And then, okay, maybe we still need a title. We can add a title. And here is our bar plot. It's made from scratch. It uses no extra libraries, no wrappers, just 5 lines of code, really. Another example. For example, you might want to produce this plot called parallel coordinates plot, which is kind of a bit fancy. So here, palette, okay, so this function, what it would do is it would change the colors represented by numbers. So if I draw a color and I say color equals 1, typically R interprets that as black. But here I say don't interpret that as black, interpret it as blue. And number 2 as red, 3 as orange. So just some preparation. Again, boilerplate, I request a new plotting region and provide a coordinate system. Then, okay, I add a grid just on the y-axis. So we have these gray lines. And then I provide this axis. The parallel coordinates plot basically joins lines for every variable. So in the iris dataset that we will use here, we have 4 variables. So I add these 4 lines that will be joined. And then I add all the lines again with a single call. Then I use this mathLines function, which draws lines from a matrix. But you can do this just with lines as well if you go over each column. So I already have the plot. Now what I need to do is just annotate it. Okay, so I add y-axis text with the axis call. And then I add text for all the variables that were used in this plot. So again, just another function called margin text. And I have my plot. Okay, maybe still I add a legend, right? I find a convenient place for a legend. And okay, one more trick here is I use factors for colors. What it does is it interprets them as integers. And I already changed the palette. So the first factor would be colored in blue, second in red, third in orange. And what this does is it makes sure that the color placement between the plot and the legend is always consistent, because factors, I never reordered them. So the same factor will always be represented by the same color. Yep, so we have another plot. And one more example is this dual coordinate plot. This is a bit in poor taste, but some people do this. You might have a plot that has 2 different y-axes. So that's an example of a plot like that. And we will be using this empty cars dataset, and we will be showing displacement on the x-axis and miles per gallon and horsepower on y-axis. So again, some boilerplate, plot new, plotting region as always. We add the points for the first y-axis and add the actual axis label. And now the hardest part of this plot is I need to add a second y-axis that uses different numbers. What do? So I change the coordinate system in the middle of the plot by calling plot window again, and now providing different values for the y coordinates. And right after that, I add my second set of points in different color, and I add axis annotation on the right side now. So the plot is already done. And now I need just to annotate it again. So, okay, I add axis on the axis values for the x-axis. I maybe add box around the plot and some annotations in different colors. Yeah, so this plot that on the first impression might look a bit complicated. You know, you need two different y-axes. If you do base plotting really from this fundamental like elements, it becomes quite easy and very intuitive, in my opinion, at least. And the final example is this correlation plot. So this kind of plot you might be familiar with if you use packages like corplot or maybe ggcorplot. And it tries to present correlation values from a data set in the form of circles. So here we will be using empty cars data set, and this cars variable just holds the correlation matrix, and calls variable in the second line, don't worry too much about the syntax, but it basically obtains a color for each correlation value that goes from blue to red. Again, some boilerplate. We initiate our plotting region. With the call to rect, we add this grid of rectangles, and within each of a cell in each grid, now we will plot our correlation values. So we do that with another function call, which is symbols. And with symbols, we can control what kind of symbol we plot. In this case, it's a circle. We can control the colors and the sizes of these circles. So in this case, I just make sizes proportional to correlation values. And we have our plot. Only thing that is left to do is just to annotate it. So we add tags for each variable, and we have our plot again in maybe 5 lines of code. The actual code that does the plot and annotation. Yep, so that's my final example. And the takeaway from this, I would say, is that base plotting has this kind of mystique about it, where users are never really introduced to it properly, I think. And it's a bit sad, I think, because really it allows you to replicate any kind of plot. So if, for example, you're working as a person who does plots for some company, and you have a designer that makes templates, and your job is to produce a plot that resembles that template really thoroughly, exactly. This type of plotting, like base plotting, I think would be the perfect tool for that, and it would just take a few lines of code. And you can actually do a lot of crazy things here. So for example, if you want to have a plot that instead of having 2 y-axes, it has 5 different y-axes, that's fine. It's just 5 more lines and you will have. Yep, so thank you for listening and hope you enjoyed. In this talk, I mainly presented some of the corners of R I found during my work that seemed interesting to me, and some ways in which I tried to utilize those corners. And I hope some of you maybe got some inspiration to try using them for maybe different purposes. I use them for providing a theming system and this package inops, but this doesn't mean that they can only be used for that. There are a lot of other users that I probably didn't think about. And this talk was mainly a compilation of 2 of my articles. And if you are interested in that and want to find even more stuff about even more lesser known features or more information about base plotting, you can check that out. So that's it.
Thank you. I think it's the end, and we can all